social blogs where people discuss different diseases. It could be the biomedical scholarly literature where the publications of the findings are published and stored. And it could also be news on CNN that discuss different health-related topics. However, a big chunk of the health-related data actually resides in the electronic health record. And I'm going to talk a lot about processing that type of data. So the electronic health record consists of two main parts. One is usually referred to as the structured database of the electronic medical record, and in that structured database you basically have relational databases that actually store values in very well-defined fields. So you will find the lab results, you will find the height of the patient, you will find the prescribed medications in the structured databases. So that data is fairly well understood, you can mine it, you can use it. However, probably 50% of the data resides in the unstructured part of the EMR, and that's the clinical narrative. So when you go and see a physician, after the visit, the physician has to sit down and write a clinical note describing your complaints, the final diagnosis, and the recommendations that actually the physician may feel. So this is the clinical narrative. And the clinical narrative can and actually spans all medical specialties. And there are some very specific subtypes, for example, radiology notes, where the center of the description is not the patient, but is the image of the patient, for example, an X-ray, or pathology notes, where the center of the description is again not the human being, but it's some tissue that was taken out of the human being and described in great detail. So you need pathology notes for cancer diagnosing, radiology notes for different disease diagnosing. So this is the data set that I'm going to talk about in the presentation. However, we are branching out to all health-related data. My background is actually linguistics and computer science. So I'm not a trained physician. I have worked with many physicians and I understand some of what they do. However, I'm not a physician by training whatsoever. And working with physicians is critical in doing good information extraction from the clinical narrative. The work that I'm going to describe was funded by a number of projects, and I'm listing the projects, different grants from the NIH, from the ONC, the Office of the National Coordinator of Healthcare Technologies, and also we had a small grant from IBM. When I was at the Mayo Clinic, there was a very big project between Mayo Clinic and IBM, and I was part of that project. And actually, CTEC started with this very small UIMA grant from IBM. I also want to acknowledge several institutions who are probably the leaders, the pioneers in making their data available to release to the research community. And this is revolutionary because this is patient data. There are many protections on patient data, so we have to go through lots of de-identification. We have to go through setting up data use agreements. However, these institutions, Mayo Clinic, Seattle Group Health, and Beth Israel Hospital in Boston, they stood behind the initiative and they actually went with it. So we are very grateful to them because without their support, this work would not have been possible. Then I want to acknowledge all collaborators. You will see the scope of the work is pretty big, and it would not be possible without all the collaborators that have been involved throughout the years. My immediate colleagues at Boston Children's Hospital and Medical School, also University of Colorado, Martha Palmer, Jim Martin, Wayne Ward, Kevin Cohen, University of Utah, Wendy Chapman, Columbia University, Noam Elpidat, Brandeis University, James Dostoyevsky, University of Alabama, Steve Fetter, and then the many physicians who have contributed also to the different projects. And the physicians from the Mayo Clinic, the Brigham and Women's Hospital in Boston, Mass General, Seattle, and Health. So we are also part of the IPD2. I don't know whether you have heard about the IPD2. It's a project to build a phenotyping/genotyping platform that can be used by clinical investigators to do GWAS studies. And to be able to do that, we have to do natural language processing of the clinical narrative. So we are part of the IPD2 team contributing to the information extraction from the clinical narrative. So very broadly, my research interests, I try to summarize them in 3 bullets, but they're very broad, are semantic and discourse processing of calculated text, also the creation of shared annotated resources and shared code, and applications of natural language processing to the field of biomedicine. So hopefully I will be able to show you some of the applications. So how can NLP help biomedicine? There is a huge need and huge demand in biomedicine for natural language processing. There are many tasks that require mining the clinical narrative in the EHR and combining it with the structured databases. You know that we are in the era of GWAS studies, where we want to identify different genes and SNPs associated with diseases, and also treatments. Some people have exactly the same diseases, they prescribe the same treatments, but for some people the treatment does not work, for other people the treatment works. Where is the key to the puzzle? To be able to answer these questions, we have to have huge cohorts of patients that are actually genotyped, so that the GWAS studies can be actually performed. So how do you get to these cohorts? One way is to actually start building the data and manually tagging each patient. The other way is to do NLP on the clinical narrative, information extraction, and discover the relevant cohorts. So when I was at the Mayo Clinic back in 2003, I was very surprised, probably shocked to learn that for this rheumatoid arthritis study, the abstractors spent 5 years to go to patient charts and identify a patient cohort to be used for the study. A patient cohort that matches certain variables. And these were teams of abstractors. So the goals, there are many applications in the clinical domain. The direct clinical practice, physicians want to see a summary of the patient's history. There are many complex patients, especially at these tertiary centers. So it's not like your primary care physician with the patient with just a regular checkup. It's patients with very complicated diseases. Some of these patients, I hear that most of these very complicated cases actually have around 500 notes. The physician has to know the history of the patient. So what they do right now is they go through the notes to establish a picture in their head of what the patient is all about. They would love to have a summarizer that they can trust and that can help them in their work. So there are many applications. I hope I motivated some of the work. So when I joined the Mayo Clinic, in the general open domain, we have all had the LDC and the entry bank for quite some time. There have been many experiments and many advancements. However, in the clinical domain, there was no such equivalent. So we started thinking about how can we actually create shared annotated resources of clinical narrative, annotated in a similar fashion as what LDC and entry bank have done. So why is that important? Because then you can merge all these resources, you can build parsers, you can do very interesting research on different topics within NLP. And actually you can do very interesting theoretical linguistics research when you merge multiple resources. So we definitely needed that. We wanted to enable the development of the next generation NLP tools for health. However, there are many logistics. How do you do this? We know that the data is patient sensitive. You cannot release the data. You have to have an approved therapy. You have the HIPAA protections. What are the mechanisms of storage and delivery to these resources? And then you have to start involving lawyers. And you have to start talking with the lawyers and come to some resolution of how this data can be made available to the research community. So these are purely logistical questions. Then the interesting question is the annotation process. Imagine that we can release the data. How can we now do efficient annotations that are consistent with linguistic theory and with the annotations in the open domain? Also, what is the role of active learning? How can we decrease the time, yet create enough annotations to enable not only supervised algorithms, but also very widely supervised algorithms and the evaluation of completely unsupervised algorithms? What can we learn from the annotation research in the open domain? Then there's another question. Okay, we will take the entry bank annotation scheme, the prop bank annotation scheme, and we're going to extend and apply to clinical data. However, there are semantic annotations that are not represented in entry bank. How do we represent those? What are the annotation schemes? What to annotate? How to annotate? So these are some of the questions associated with the annotation of the data. Imagining that the data can be released to the research community. So, and this is work, I should mention, done with Mani Alcadat, Wendy Chapman, Martha Palmer. So the guiding principles that we came up with were several. First, we have to do general purpose annotations. We didn't want to do use case specific annotations. For example, this physician is interested only in colon cancer, so we are going to do only annotations relevant to colon cancer. We wanted to create schemas that actually apply to every, if not every, 99% of all imaginable use cases in the clinical domain. We also wanted to leverage established conventions and standards whenever possible. So take the entry bank, annotation guidelines, apply them to a clinical domain, extend where needed, but still conform to entry bank. We did that with Canada as well, and we also used previous semantic schemes. At this point, we made one decision to avoid inferencing whenever possible. So we are not annotating inferencing. We are annotating only explicit annotations. Another principle is to do the layered annotations. So you have the annotations of tokens, part-of-speech tags, the syntactic trees, the prop bank annotations, which is the predicate argument structure, and then the domain-specific annotations. So So what does that give you? For example, if you're interested in parsing, you can use these annotations to do parsing research. If you're interested in semantic role labeling, you can use the annotations to do your research in that. So we believe that it enables a lot of different and varied research plans. And we also made the decision that we have to accept that not everything can be annotated at this point. So probably 10 years from now, we will annotate everything that is in the clinical node, but at this point, we decided to stick to the most important annotations that will cover 90% of the use cases. So these are the guiding principles, and I'm going to briefly talk about some of the shared annotations, annotated resources that some of them are available right now, so you can get them, and the others will be available very, very soon, by this summer. So the first effort is the SHARE project, and that stands for Shared Annotated Resources. It's funded by NIH, and the research focuses to develop annotation schema and guidelines, annotation process and workflow, and organize shared tasks around these annotations. So what are we doing? What types of annotations we are providing? We have a 500,000 word corpus, and we are annotating syntactic information and also clinical entities. Clinical entities are diseases, disorders, as defined by the UMLS. How many of you are familiar with the UMLS? Okay, so UMLS is an ontology of classification from the National Library of Medicine. It stands for Unified Medical Language System. In the medical domain, unlike in the open domain, there are many classification schemes. Physicians like to have classifications. They like to classify diseases by domains, and then from the very general disease to the more specific disease. And they have organized them over the centuries, actually, into these classification schemes or ontologies. So what UMLS, and there are about 140 of these. The most dominant one is SNOMED-CT. So every physician uses SNOMED-CT. So for example, the rheumatologists that I'm working with, they know the rheumatology branch of SNOMED-CT. And they know which disease is under what disease and how the branch works. So UMLS combines all these 114 medical, biomedical ontologies and builds one ontology, one classification that can be used as a reference, and also cross-mapping between different ontologies. So you will find gene ontology, disease ontology, cancer ontology, functioning, patient functioning ontology. That's very important. Whether the patient bakes by themselves, eats by themselves, things like that. So, and these ontologies, they define the main entity mentioned, types. For example, diseases, disorders, signs and symptoms, anatomical sites, procedures and medications. So we do not reinvent the definition of these main semantic types. We use the UMLS to actually type dimensions. Also, there are several semantic modifiers that are of great importance for those entity dimensions, and I'm listing all of them. I want to pay special attention to the negation indicator. Negation is extremely important. Physicians, if something is negated, if something is not present with the patient, physicians do explicitly state that. The patient did not experience pain. So you know that the patient did not have pain. And that's a very important fact. The negation of that mention is a very important fact for the patient, for the physician. Also, the subject, or the experiencer, which is one of the prop bank semantic roles, Art 1 is very important because there is a lot of medical history in the clinical notes. Let's say father had cancer, mother had diabetes. That is very, very relevant. So we have to discover this very quickly.
So, for the semantic modifiers, then are these for the experience, imputing the severity? Are you saying there are automated, regular expression or dictionary type elements that are used to be able to do that, and that's not part of UMLS?
No, UMLS gives you only the mapping of a disease to a code.
Got it.
This is the annotation schema that we're using to share. And then, so these are gold annotations annotated by two domain experts followed by an adjudication process. And then you end up with a gold standard. Then you take the gold standard and you can develop modules to actually automatically discover.
Understood. And there are existing modules to discover existing right? In addition to the gold standard data?
So we are in the process of building modules, and most of them are implemented in CTEX. So we have modules for the everything except, I think we have modules for everything.
Okay.
Yeah. At this point. Yeah.
So maybe I shouldn't ask because you have your honor, but I've been hoping for a while that you're going to show us some actual natural language from patient records so we can see what the data look like. Are you not allowed to show us?
To the lawyers, Judith.
I'm going to show you, yes. So maybe I can just briefly tell you, yeah.
Do it to the lecture.
Okay, so tell me what you're most interested in, and maybe I can do it that way. So I have prepared these shared resources. Then I have some methods for the temporal relation extraction, which I think would be very interesting.
I think Jason just wants everybody to kind of get a look at what an EHR clinical text note looks like, and then everything else is as all the other topics that are addressed.
Yes, I mean, it's also very interesting to see what you annotate.
So
you started your talk saying these natural language data look different from the natural language data you're used to. So
okay, so maybe I can show you. Sorry.
Do you have an example of an EHR
Yeah,
summary?
that's what I'm looking for right here. And that's an excellent point that I should include that in the first, probably one of the first slides, because I just assumed wrongly that this is team. So this is an example of actually a colon cancer note. So you will see. And
this is actually much more fluid than I would have expected. That may have to do with this particular example or with the transcription.
Usually what I hear from physicians is that for the more complex cases, and this is a complex case because it's cancer, the physicians write really well and they're motivated to write very detailed notes. They do not take the documentation part of cases, complex patients write. It's different if it's a primary care physician now for a regular checkup. But it's a very good point that I should include in my presentation, just a snapshot of a clinical note. This is an example. So let me go back. Okay, and I'll just go very fast through the annotated, the shared resources, because I want you to be aware of this, so that you can actually download, fill out the data use agreements, and then download. So the share status, we have 400,000 words that are completely annotated, so we are almost at the end of the project, double annotation followed by adjudication. This year, the 2014 Semi-Val Task 7 actually uses the corpus. So if you want to enroll and participate in Task 7, that's what you're going to get. We are also submitting a proposal for 2015 Semi-Val around the same corpus. So if you're part of Task 7, you will get the corpus and the annotations. The multi-source integrated platform for answering clinical questions, that's MyPact. It's another resource, it's available now. So if you want to get access to this corpus, send me an email and I will tell you how you can fill out the data use agreement and download the corpus. So you will get tree bank, the layers, the annotation layers, the tree banking, crop banking, UMLS entities and modifiers, UMLS relations and modifiers, and co-reference. And that's compatible with share. So you can combine the two resources. We have a paper describing my path. So these are some of the characteristics. So it's about 30,000 named entity mentions. The agreement results are fairly good. So you can build models, you can do research with this type of data. And there are some more characteristics of the distribution. So for the semantic roles, you see that the arc 0, which is the experience usually, is the dominant one. And then the other arcs are also represented somewhat. Then the UMLS semantic groups have that representation. I'm not surprised to see that procedures and disorders and signs and symptoms are at the top, because these are the most requested entity types and the most informative entity types. So that corpus is available right now. We are just finishing packaging the sharp corpus, and that's an additional 500,000 words. Again, layered annotations. So if you do the counts, by now we have at least 1 million words of annotated data, which is pretty much the size of tree bank.
So 500,000 words, how many different cases does that represent? Or narratives does it?
How many documents? So actually what we did a random representation of the Mayo Clinic EMR to this corpus. So we pull randomly from different specialties. So it's not a longitudinal representation of one patient. It's more representation of the language from different specialties.
And how many words does
How many documents? In terms of documents, 2,000.
So it's a lot of words per document.
Yeah.
That leads to a question: if the documents are long, is there a cross-sentential structure like the document co-rep?
Yes.
And is the co-rep just at the level of named entities, as is common, or does it refer to the development of a particular hematoma, which is mentioned here, and then again later?
It's at the level of the entity mention, but you have the entire chain.
Are the entities limited to named entities, or do they include diseases, body parts, symptoms, and other things where you might have co-reference?
So the entity types are diseases, disorders, signs and symptoms, anatomical sites, procedures, and medications.
Fantastic.
And now we're doing event co-reference as well.
That's great. So this is really quite an achievement to have built this. There's an obvious question that you might not have the answer to until after you release the corpus, but do you know what happens if you run standard NLP tools?
Yes, we have done that, and actually we also trained models, and they're released as part of CDEX.
Yes, what I mean is you do cross-down, you
yeah,
train for
yeah,
it.
so we have done that. So, and I should have the data, but it's not in this presentation. So I remember that there was about 20 percentage points gain when you combine this data with the tree bank, with the OMC data.
Good, so having in-domain data is good. And how much, if you train and test on tree bank data, and you compare that to training and testing on this corpus, for the comparable amounts of data, is the performance on this kind of data better or worse?
It's better. And we did all these experiments, yes.
So in some sense, so one might think the clinical narrative is more difficult, but because I've heard many things about how difficult this stuff is. But maybe if you have the right kind of training data, it's actually easier because the domain is limited, and there's various kinds of conventional language that's used over and over again.
Absolutely. Yes.
Thanks.
Yes.
Do you think the 2,000 documents, that's a sufficiently large enough size corpus to
So when we started the experiment, we had only the MyPath corpus, which was 1/5 of the size of this. And with that small corpus, we immediately saw things. So even if you infuse just a small amount of domain data into your data set, you get things.
Because you have to divide this up into training
Yeah, and
parameter, setting the
Absolutely.
parameters and then
And
the
we're
test
very
set.
meticulous about it, yes, yes. And we have done the splits pretty much in the same fashion as the 10 tree banks, so we know that this is only for testing and you don't touch this, and this is only for development.
Within the U.S., clinical notes are standardly in English, they're never in any other language.
Correct. Okay, basically what I'm showing here is entity-mention annotations and then relation annotations, because in these data sets you are going to see relation annotations. And again, the definition of relations is through the UMLS. We do not invent any of the definitions. Then there are the templates. So each entity mention has a template and modifiers associated with the templates. And that's what syntax pretty much discovers. So at the end you have an entity mention and the template populated to that entity mention. So the last resource that, wow, time is flying. The last resource that I would like to mention to you is the time resource, temporal histories of your medical events. So now on top of all these annotations, we have the temporal relations. We have events, temporal expressions, temporal relations, and event correctness. That corpus will hopefully be part of 10th Eval 2015. We are submitting the proposal, and hopefully it will get accepted, and you will see the corpus there. The annotation guidelines are an extension of ISO TimeML. Okay, so I will skip this. And some examples of how it's annotated.
These are going back on the same central notes but adding time annotations.
And actually the temporal annotations are on notes from the colon cancer and the brain cancer domain. So now we are adding oncology to everything else. Because there is a lot of work in data mining in oncology. So we are thinking if we can help discover the treatment of cancer, that would be great. So temporal relations in clinical notes. So this is just one of the topics, methods, related topics that I'm going to very briefly discuss. Temporality in the clinical domain is very important. Medication start and stop dates, procedure frequencies, disease onsets, data mining of typical timelines. It's very important at the single patient and cohort granularity levels. So for example, we have been doing work on a phenotype that is called liver toxicity, which is the abnormal functioning of the liver, and actually that can be caused by medications. So how do you know that the liver toxicity is caused by medication and not by other factors or other comorbidities, other diseases that the patient has? So this is very temporally sensitive, and we have been using our methods to help mine the EMR for this phenotype. Okay, so I will skip this. These are the typical temporal relations before overlap, begin zone, end zone, and contain. And I want to focus on a new representation of temporal relations, and that's called the narrative container. We have a paper out, and it's the Miller and al. 2013 paper. It was presented at the ACL last year. So if you're interested, all the details are in that paper. So narrative containers are these temporality-related expressions that hold many events. So for example, you can say, on Tuesday I went to school, then I went to the library, then I went to the grocery store. Tuesday becomes an anchor or the narrative container of several events. And you associate went to school, went to the library, and did grocery shopping with that narrative container. Now, instead of explicitly pairwise linking all the events, you create these narrative containers, and they actually help you later on define a very defined timeline. So this is a very new concept in representing temporality. So it's in between, there you have temporality, just before and after, and very fine-grained temporality. And we believe that this representation actually helps fine-grained temporality. So here's an example. I showed you this text before. So it's a text from an oncology note. And in that text, we see several narrative containers. September 1st contains the events of developed and blood. And actually, we are annotating only the headwords. So that's why it's blood only. September 3rd anchors the colonoscopy event, and so on. So now the question is, how can we find these narrative containers? What are the computational methods to find them? Nobody has done that. So our approach, and that's described in the paper that I showed you, is to cast the problem as a classification problem, where we take every temporal expression, and for each event, we classify the temporal expression and the event. And then the classifier tells us whether the event actually belongs to that narrative container. Okay, that seems straightforward, but how do we do that? So now we know that the devil is in the detail. What are the features that would make a good guess at solving the problem? So in the temporal relation domain, there are a number of what we call flag features that actually have been used quite a lot. And I'm listing the flag features that we experimented with. These are usually the tokens, the part of words tags in both arguments, the tokens around the arguments, the tokens between the arguments, the distance between arguments, and contextual modality modifiers associated with the events, as well as the time class associated with the temporal expression. Okay, this is known. Pretty much everybody in the temporal community did this. However, we felt that we have that structure can be very informative in discovering the temporal relation, the containers. And we especially zoomed in the tree kernels as the structure that will provide us power to discover the containers. So the tree kernels, they were introduced by Collins and Jeffrey in this paper, and what they are is a syntactic representation. We take a constituent for a tree, and then we break down that constituent for a tree into the subconstituents, and this is one example of how we do it. So now you have a representation, and each constituent, each subtree now becomes a feature to the tree kernel. So this is the main idea. And you can, so we have now on one hand the flag features, and on the other hand we have the tree kernels. you can combine the two still in one kernel, and these are called the composite kernels. We actually use a tool by Muschietti to do the combination, to do the three kernels and the combination of the three kernels. However, this is still not an answer to the question. Now, the next question is, okay, how do you represent the tree? There are many ways that you can represent a syntactic tree. What would be the best representation, especially combining with the flat features? So we found only two papers that actually tried this approach. The first one is the Covey paper, and this is what I'm showing you. And they used a very simplified way of representing the tree. So it's called bag of words, part of speech tags. So you see it's a very flat structure. For those of you who have taken syntax, you know that syntax usually is not represented that way. And in their paper, they said that this flat structure actually introduced performance improvements. However, using the full structure, the full syntactic structure, did not improve the results. So then there is this representation, which is called the path enclosed tree, and this is a subtree of the main tree, and it takes only the path between the two arguments. So in this case, we have the path between the event of schedule and the temporal expression of next week. You're not taking the full tree. And this is the path enclosed tree. And another representation is the path tree, and that's used in semantic row labeling. And this is a subset of the path enclosed tree, with the difference that you take only the nodes that are on the path between the arguments. So in a way, it's a simplified tree. I want to point, where do we go? Okay, so Mule-Chandel is the second paper that actually experimented with temporal relations in tree kernels. And they reported, unlike the Covey paper, they reported positive gains when tree kernels are used. So our question is now, well, if we apply this to something similar to the clinical data, would we see improvements? And actually, what is the right syntactic representation to feed into the tree kernel? We use the temporal, the time corpus, and we have two baselines. One is the high precision baseline, which links every time to the closest event. And also we have a high recall baseline, which links every event to the closest time. And we did all the bit searching on the development set. It was very carefully and meticulously done. So here are the results. So first the two baselines are the first two rows. If you use only the flat features, which has been what the community, the state of the art in the community, you get an X score of 0.645. If we add the Covey style tree, which is just a bag of words, if you remember the very simple structure, then there are some gains, about 4 percentage points. Now, if we add the path enclosed tree and the path tree, this is the best combination. If we substitute the path enclosed tree and the path tree, we get the second best result, and that's 0.691. And I guess that shows us that at least with our data, the tree kernels and the representation of the structure between the arguments really works. And this supports the Mule-Chandel result, and this contradicts in a way the Colby result. And we suspect that the Colby result is not that good because of the impoverished syntactic structure that is represented in the spread in the tree climate. So this is a flavor of the methods that we are developing for semantic processing, and specifically for temporal relation extraction. We feel that these methods are probably portable to relation extraction in general, and we are experimenting with other types of relations besides the temporal relations. So I will very quickly go through this. One interest of mine, research interest, is actually building large-scale NLP and information extraction systems, applying them to various use cases in the domain of biomedicine. I will skip all this motivation of why we need that, and I will focus on the system that we have been developing, and that's CTEX, and it's now part of the Apache Software Foundation. So all these annotations and models that we have built and research that we have done, we release into the Apache CTEX. So if you're, for example, if you want, for example, to use some of the parsers as enabling technologies for your research, you can just go and get the CTEX parser and use it as long as it conforms to, I guess, the output. You have to do some post-processing of the output. So this is the URL to CTEX, ctex.apache.org. There is a very active development and user community. I'm going to skip all this because we don't have time. You can subscribe to the mailing list, and you will find that on the Apache website. And here are the current components in CTEX. Again, all of them are trained on combination of tree bank data and clinical data. So you have the sentence boundary detection, tokenization, morphological normalization, part-of-speech tagging, shallow parsing, named entity recognition, assertion module to discover negation, uncertainty, the generic use of entity dimension, conditional, dependency parser, constituency parser, semantic role labeler, a relation extraction module, co-reference module, and the drug profile module, which gives you the attributes associated with the drug profile, and then one module that is by popular demand by clinical investigators, and that's the smoking status classifier, finding out whether the patient actually is a smoker or not a smoker, because that's a very important variable in disease investigation. And the last one is a normalization module, so this is filling a template for every entity dimension with all the attributes associated with the entity dimension. So it's Apache license, you can go, take it, contribute if you'd like. These are some details from CTEX. Applications in biomedicine. So probably you're wondering, how have you applied all this to biomedicine? We have applied it to translational science and clinical investigation. Patient cohort identification is a very popular use case. So at Mass General and Brigham and Women's, there are 6 million patients, and we have requests from different investigators. I want to study patients who have autism. Can you find a cohort of 10,000 patients with autism? And we try a combination of ICD-9 codes, which are billing codes, and mining the clinical narrative using the output of CTEX, and that's how we produce the cohort. The expectation is that the PPV, the positive predictive value, or the precision, should be at least 0.8. So the clinical investigators are very firm about this. And we are also part of eMERGE, where the PPV is set at 0.9. So an algorithm actually will not make the cut and will not be used if the p-value is below 0.9 millimole. Comparative effectiveness is another very high-profile topic. So what is comparative effectiveness? Means what treatments actually work compared to other treatments. And that to know that requires the study of large patient cohorts. So there is a lot of effort of finding the most efficient treatments for different diseases. And that falls within comparative effectiveness. Epidemiology, finding flu outbreaks. John Brownstein, a colleague of mine at the medical school, he had created a health map, and he tracks instances of flu outbreaks, and that map is constantly updated. And actually, it's now used by the CDC to track disease outbreaks. So this is all relying on mining the clinical narrative. Okay, so I will skip this. And I just would like to briefly mention, which you're going to use another couple of minutes, the phenotyping, how we do the phenotyping. Because there is a lot of machine learning expertise here in the room, and Hopkins in general, and I think this would be a topic that would be of interest to you. As I said, our starting point is the entire EMR, and we have to mine for different phenotypes. Let's say rheumatoid arthritis, multiple sclerosis, autism. So there are these ICD-9 codes which are used for billing. So every clinical note is coded for ICD-9 codes, and then these codes are sent to the insurance companies, and that's how the hospital is paid. However, the ICD-9 code is not the final diagnosis. So for example, if you have an ICD-9 code for rheumatoid arthritis, it does not mean that you have the disease. It means that you were probably evaluated for the disease, and the physician needs to be paid for that evaluation. It's a different story of whether you actually are diagnosed with the disease. So they cannot be relied on. They can be used, but it's not PPV of 0.9. So we use that as the initial filtering to get a smaller subset of the patients. Then we extract the information from the clinical narrative and convert it and represent it as vectors, feature vectors. We apply feature selection, and then we build classifiers. The physicians, unfortunately at this point, they still have to label some data for us and say, okay, this patient has had RA, this patient didn't, which we use to train a classifier. And we have developed a number of phenotypes that are currently being used. So, obviously there is a lot of information that I presented to you, and this is my last slide, and I just want to throw even more to topics of interest, and these are research topics. So shared annotated resources, active learning. You don't have to do this manual annotation all the time. How can we use active learning? And we have started looking at that. How can we efficiently, intelligently get only the most informative instances for the training? Then can we move from the paradigm of supervised learning to lightly supervised or even completely unsupervised methods for semantic processing? And we have started working on that as well. Then we have great interest in joint syntactic semantic models, not this 5 points stepwise approach. Word sense disambiguation. That is a huge topic because many streams map to many concepts in the UMLS. So the sense inventory is the UMLS. So how do you find that MS actually refers to multiple sclerosis and not to morphine sulfate? This regulation. Co-reference, very important. The cancer group. Which cancer was it? The cancer of the father or the cancer of the patient? Discourse relations. Patient vomited due to aspirin. What was the cause of the vomiting? Or patient had a heart attack because they were on Vioxx. If you remember the Vioxx study from several years ago. Question answering. Then large-scale phenotyping framework with minimum supervision. Obviously, software engineering for large-scale enterprise NLP and information extraction help. Because we process for type 2 diabetes, we have to process 30 million documents. And the physician just could not wait 1 month for these notes to be processed. So how can we decrease the processing time and have enterprise solutions? They don't care about our parsers, the end users. They just want their notes like processed in a day. Then can we build an NLP ecosystem that everybody contributes to and does very interesting research? Another very important topic is the visualization of the output. And especially with the temporal relations, the physicians want to see the timeline. I skipped over that slide. That's something I cannot stress how important it is for the end user to have something to visualize the output with, something that makes sense. And building buoys and building visualization tools is a completely separate area of research, and I'm not an expert, but I'm a user of that. So we have been working with University of Maryland, Ben Schneiderman's lab, on visualization tools, especially for the temporal relations. So I think that's pretty much it, and we are 5 minutes over time. Any questions? Or any slides that you would like me to go back to and explain more?
So when I have one which is the big question, and so when you guys managed to release all that text publicly, did someone have to go through each one of the texts annually to make sure it was completely de-identified?
Yes. It's completely de-identified. We used an automated tool to do the first pass, and the second pass is manual pass. Otherwise, they would not allow us to.
And then for many of the tools you mentioned, Guergana, I'm curious from your experience of applying it to a variety of applications. So I've had some experience playing with it, but curious, do they often, in your majority of times, are you seeing that you're able to get pretty great results from just out-of-the-box implementation, or you're having to do tweaking or training that's specific to that domain?
We usually don't do any tweaking. So for the phenotyping algorithm, we do some tweaking. But we take the output of CTEX, we build the feature vectors. We do not do any tweaking on the NLP components. The tweaking is more, do we filter by this ICD-9 code, but not by this code? Do we take notes only from this clinic, but not that clinic? Things like that.
So, on your last slide, you talked about semi-supervised billing or lightly supervised billing, and I was wondering about the structured information that's also in medical records. So I think you said earlier that you deliberately avoided looking at that at this stage, or doing joint reasoning over the structured data and the text. But it's not obvious to me whether the information in those two things is redundant or separate? If it's separate, is it at least correlated in a way that would allow you to use that to help bootstrap semantics?
Yeah, that's an excellent question. So we have not done systematic study on that, but that's exactly where we're going.
So, we did actually consider that. So this was, I think 2 to 3 years ago, we published a study trying to do patient outcome extraction and seeing how could we leverage the structured data to make better use of the unstructured text data and vice versa. And we compared with the I2B2 task winners as the baseline and showed that you can actually improve by quite a bit using very simple ideas from machine learning. So I think that's an area where there's definitely, I think, really good for improvement.
So you believe that there is overlap, that there are things that are being that are expressed also in structure?
It's kind of, you have basically correlated information, which is very helpful in this ambiguity table. So for example, the cases where something is being negated, but the language doesn't make it very clear, but the lack of correlated information in the structured data makes it clear. Or the presence of structured information suggests that perhaps this event did exist even though the language is ambiguous around whether or not the event existed. So in these, the results actually improve quite a bit in considering them jointly as opposed to one or the other.
And the ICD-9 codes, although they cannot be 100% trusted, which is that they can be used for disambiguation to an extent. So if you see in the text MS, and you don't know what the MS refers to, you can probably use the ICD-9 code to understand whether it's multiple sclerosis to make a guess.
If there's an ICD-9 code, why would they bother to say or write multiple sclerosis? So when I said that there might not be redundancy, I was thinking that maybe the notes, that the narrative that they give is only filling in stuff that there wasn't a checkbox for.
No, actually the ICD-9 codes are derived from the note. So physicians who write the note, and then there are coders who read the note and code.
And that coding is free annotation because it was done by humans outside your project?
Yes.
For billing purposes.
For billing.
Yeah.
But also when I say structured information, I don't just mean IC9 codes, I mean medication.
Lab results.
Any lab results, any orders that were made. Basically patterns of treatment or patterns of measurements that are equally indicative of disease, even though they weren't mentioned as structured.
Well, so we can take this discussion offline. I think people probably need to.
Okay.